Hi everyone, this is another update on more tests. This was my first configuration here with the neodymium magnet there sandwiched in between the two I-cores. And what I decided to do is come up with another kind of configuration, which is pretty well based on Thane Heins bitoroid transformer configuration. Because here I've used the balance of C-core that I had made, which is basically a microwave oven transformer E-core that I've taken the center out. So here you see the C-core going across there, and I have two high current coils that are wound on it. And this wire here that I used on this first test configuration is 8 millimeter, probably like a 22 gauge or something like that. This one here is really thick wire. You can see it there from there. It's 1.6 millimeter wire, so very low DC resistance, and that's what I wanted to see if this effect had something to do with a high voltage coil, because this was putting out more high voltage than current. And I want to see if high current, low voltage works just as well. And I can confirm actually it does. And it does because of connecting it in the bitoroid transformer configuration, which I will go over with you on that. So again, here's my double rotor, so double C-core rotor that I made. And right now this is away from the head here of the drill press that I'm using as a prime mover. So I'll give that a start, and we'll look at how much wattage that will take just to turn that with this away. And here you've obviously noticed that I have a neodymium magnet here, the same size that I had inside here, underneath the C-core here. So it's magnetically stuck onto this plate here of the drill press, and I have super glue there, and I also have super glue here on the edge to hold this into place a little more securely. So there's a side view of it as well. And this is the only magnet wire that I had available that was in this heavy gauge. So it doesn't produce very high voltage, but same amount of power basically is what this was doing as far as wattage is concerned. So let's start it up. So I do have the variac hooked up so that I can actually drop the voltage of that induction motor to consume the less amount of power as possible. And that's what we're consuming there. About 48 watts for sure, and that's what we'll use as our baseline. So 48 watts just to make the drill press turn with this rotor on there. So now I'll bring up the core, and we'll see how much wattage the core consumes. Okay, now we have the core back up, and right with a very small air gap here with our double C-core, and as you see it's magnetically coupling. And since I have the variac dropping the voltage to the induction motor is just at its point where it could operate at minimum input power, and basically any load that we put on it is going to reflect back to the power meter. So that's why I'm doing that. So we're ready to start this now. It won't start on its own. I'll have to give it a spin to get it going so that it gets underway. So there it is now turning. And if we look at our power meter, this is the consumption. So we're about at, it'll actually drop more in the 58 watt range. Once it's, there you go, once it's warmed up a little bit. So we are now consuming 58 watts. So at first we had 48 watts with it away from the cores, and now we're at 58 watts, and the coils are open right now. So we're actually huge improvement. We are only, we have 10 watts that we are firing in the cores right now, and that's a good thing right now, because we're with this core here, if you remember, we're somewhere around 30 watts, and that was questionable. So we've dropped that significantly by going to this core configuration. So the next test now would be to put the load on. This is a 1 ohm load, the same 1 ohm load with my scope across it. So we'll go ahead and connect that load. So we are now, that load is connected, and that is our sine wave there. I'll try to give you a few less samples here so we can look at it a little closer. So there is the sine wave that we're getting across that resistor, and that is the frequency there. And I'll give you a better idea of what the true RMS value is by giving you more samples here. Okay, so right now it's saying about 2 volts RMS across that resistor. Now if we go and we look at our power consumption, we're around 61 watts, so we've gone up 3 watts, and we're delivering a little under 5 watts here. But the interesting thing though is, so we are at 61 watts. The interesting thing though is, just like when Thane basically shorts out one of the sides of his bichloride coils, which I'll do right now. I'll take this lead here and I'll create a short right here. So that coil now is shorted, and if we look at our power consumption now, we're pretty well back down to our 58 watt range. So we're not quite as low as exactly 58 watts, but not very far from that. But the other bonus that has happened now is, if we look at our voltage across our load, our voltage has gone up. So we're at 2.3 volts RMS now. And if we do our math on that, I put it at 2.24 at 1 ohm is basically exactly 5 watts. So we are dissipating 5 watts in our resistor here, and we are consuming only about 58 watts now in this configuration. So I thought this was worthy of demonstrating, and thanks for watching. Bye now.